Okay. I'm going to talk about edge detection today. So, and so I guess to start with, like, we don't have many people yet, but let's say a review. Like, so far, I guess, to do like filtering or like you think of the convolution, even though like we explain when we first explained that, like we talk about describe that as a actually we explain actually the correlation instead of like convolution. But as you know, like convolution is just flipping the filter. Right? So if you have a filter, it's originally like that. So if you are going to do a convolution instead of correlation, you just flip this filter, like both vertical and horizontal, and then apply correlation for that. So okay, anyway, so like maybe a quick test of your understanding so far. Uh, okay, let's try. Let's see. Maybe just try we have lots of combination here, right? So uh where do we get h? What is h? Do you know? Like it's a convolution of two things. So can you tell like where h is coming from? So this is like a first question, I guess. I okay, let me if I can write here, even though it's really difficult to write here. Mm, so I have this. Uh, okay, I cannot actually. I need to use the mouse for some reason. Okay, let me try that. Uh, this is a question here. H is equal to something convolved with something. So what is that something and something? H is equal to, okay, I need to feel, oh, okay, I guess I should just add a test or something, but I don't know. Okay, meanwhile, like you can see my skill of using my mouse. It's amazing. Uh, okay. I mean, it's so stupid. Like I have this what is that? Like this input device that I can write, but not writing on the PowerPoint somehow. It's so weird. So anyway, uh, anyone anyone still here? Okay, I have one response that I don't know. So it's like um good. That's like okay. Someone give answer. That's it's happy to be, yeah. So okay. Yeah, it's right. Yeah, so you have this is actually just this apparently is just a low pass filter, right? So I have this original image and go for a low pass filter. So this is just a Gaussian filter. This is a low pass Gaussian filter. And
Someone mute, please.
how about G? Like where G is coming from? Oh, oh okay. Wait. No, I'm not mute. So okay. I thought like I mute. Okay, anyway. So um I thought I muted. So okay, so what's G? Okay, this is second question here. Again, like it's a test of my amazing like mouse skill here. Uh this question two here. G is equal, wow, that's I missed that. I'm sorry about that. G is equal to uh what convolved with what? So because these two questions are so close, okay, you guys, if you just answer the first question, you may want to put a two or something. Just I know we know that like you're answering for question two or something. So so where's G is coming from? Actually, it's a good guess. I guess I will give you guys a some. extra credit for that, but not the full credit if you think it's like D kind of like come off with B. Um, uh, D come off with A and C. That will be very complicated. So if you come off with A and C, you have a combined filter here. Basically, yeah, it's kind of possible. Like we smooth this further. Yeah, this kind of okay also. Convolution is I remember is what's that called, like associative. So we can first say if you converting like D to A to C, you can first like consider I'm actually converting with the combined filter of like A and C. So then I will have yeah. So but actually maybe I will, yeah, maybe I will, yeah, some of you get it right. So at this A is actually like coming from like converting B and C actually. So you can think of this as D convert with A or like D convert with B and C or something like that. So but D convert with B is a good guess also. Like it's actually, if I don't know the answer yet, I may guess this also because even though it's smoother than probably like yeah than that. So this is basically the outcome, I guess. Where is that? It didn't. Wait. G. Yeah, yeah. G is like D and B. Yeah. Okay. So that's it. So let's start talking about edge detection. So start just a overview. Okay, everyone know about edges. I don't think like there's a need to talk about like. So this what we mean by edges is like this, right? These are the edges, and something interesting, like this is a very famous experiment that by Hubble and Wiesel. They got a Nobel Prize for in medicine, like because of this work. Basically, they're trying to probe into the brain, the neurons of a cat, and they try to see like okay, just let the cat to see this kind of joke like horizontal bar or not exactly horizontal, but kind of like incline at different angle. So and then like they pop into a particular neuron. So what they find is like okay, for a particular neuron they're probing, uh, they have some response only up to a certain angle, something like that. It will respond to this horizontal, for example, will respond to this vertical stroke, uh, but vertical line, but not the horizontal line. So it's only to some particular angle. So so that gives some hints that like we are actually sensitive, like my brain actually or your brain also. Uh, so I have a private message, just wait a sec. So D A because D B because D B also, yeah. Let's go back. I forgot like what is D A here. So D A, yeah, D B is actually D B will get something like much more noisy. Here, like it looks like very much smoother. I will give a kind of a demo like at the end, I guess, but I don't actually. But let's see. Yeah, let's see if I can do that. Yeah, but if like I have D to B, it'll be very lot a lot more noisy. The one it will still look like this, but you will see like lots of other lines there. So it, for example, like you won't see just a couple. Then you won't see it here like almost smooth here. Most likely you'll get lots of kind of like some lines here. Like okay, he's trying to catch all the horizontal line, right? So you will also see yeah a lot more like fine horizontal line basically. Here is I just move out a lot. Yeah. Um no, it's D is B. Uh it's not GB, yeah. It's DB, yeah. D and B. Oh, okay, yeah, you are right. Say that D and B. Yeah, maybe you are right. I'm sorry about that. Yeah. G is I'm kind of like okay. Yeah, you are right. Okay, the slide is D and B. Yeah. So this one, so I thought like it's more smooth out. So I guess it's not showing here. Like if D and A then will be further more smooth out even then. Like, so yeah. I thought like it's D and B. So it's hard to tell. Therefore, like both of them will look like this. but one of them is much more smooth out. Like you have like less horizontal line got catch. Yeah, then I guess it's probably D and D star with B. Yeah. Yes. So this kind of stuff, like, yeah, it's tricky. Like, yes. So okay. Or like maybe we can do experiment. Like, just this is easy to do. Like if I have time, like we have time, we can do experiment just after this. But yeah, okay. Let's move on first. So okay. We're talking about the hustle and this couple Wiesel experiment. So yeah, so we are kind of sensitive to edges basically. There's some special place in our brain is trying to handle edges. This is another experiment done like more recently, about a decade ago. Um, the main thing is like also like if you they try to pop into the response. Okay, okay, okay. Whatever. If you want to like put back the answer again, that's fine also. Right? Yeah. So yeah, and 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 yeah. That's basically, yeah. What I'm saying here is like you if you pop in the brain, like just have the test subject, like look at like photo like of the original photo or like the photo extracted just the edges. They have similar response. They are not identical, of course, but they have similar response basically. um and of course, like this is another argument is like if you just start from edges, you can just generate back the original image, at least like with like very kind of like high precision. So for example, this is the original image there. So you ended up with these edges, and you did a bunch of processing, assuming the lighting and so on. You get back something like this. So pretty similar to the original image. So therefore, edges have lots of information, and so in terms of like just for computer vision, like we want to have edges that use that as for pre-processing, and also like yeah, from pre-processing we can after we get the edges, maybe we can try to estimate the geometry, like the 3D geometry of or like of the object itself. So maybe like it may not be that easy also. Yeah, this is kind of idealistic, honestly. Um, at least like for current the state of the art, if you want to estimate the 3D shape or something, like typically you don't do like along this line. At least this is not the line that gives the best performing the state of the art result. So so where edge is coming from, this is apparent. Like you, if whenever you the object have the transition, you may have the edges. It can be like color change. It can be um, like shadows. Like for example, you have this object here, even the same color, but like because like it's this one is I mean, if they are attached to one another, of course, like this edge does not appear as apparent. And or like maybe I can just have like the same cup, like same surface, but I have different transition because of the color. And okay, in terms of like uh, the kind of trying to estimate an edge. So what we can think of, like for example, if this is an edge here, if we just like look at the signal, the intensity here. Here is a black and white image, so I only care about the intensity. If I go along the line and I plot the intensity, I will get something like that, right? So, so therefore, like basically, we are looking for the transition of the object. Okay, basically, that's actually maybe one thing is good. Wait, just wait a sec. Let me. Where's my? Oops. Did I close that? This is very confusing here now. Why yeah I oh by the way, okay, maybe a simple question. Wait a second. Let me make a simple question again. So just uh, So you did this, you should know now. Okay, oh, okay. I need to start this thing to use my pen. Or did I have a typo? Okay, it should work now. So if I have edges, okay, I will just restart sooner also for some reason. Oops. So if I consider edges, okay, this is a simple question. Like for example, I have edges here. So the edge here, is this a low pass or high pass component? Okay, that's good. Yeah. By this time, you guys should be okay. So okay, maybe then one idea, honestly, even look at like what's the edge detection. One idea, like okay, maybe what we can do is like we can just like do a high pass filtering to extract the edges, right? And actually, I want to show you this, but I need to find my. I don't know why it disappeared. Oops, I cannot. You don't know what I'm doing, but actually I'm doing like something in the background of another screen. Um, let's see. Did I close it somehow? It should be still a while. I don't know where is it. What is that? Okay, why I log out Jupyter? That's so weird. Okay, let me start Jupyter also. Sorry for the technical difficulty for the moment. I better find my. Okay, it's fine, I guess. Oh, that's quite weird now. Okay. Let's see. Yeah, I try to save everything into one file. It's getting too big. It's a little bit hard to find. Okay, I think this hopefully okay. Yeah. So let's start with another camera. Okay. So remember I show you this way. So this is the high pass filter here, right? This is doing high pass. So I can do a little bit of edge detection also. You can see like, so it's not so nice, but it's like, okay, not this camera I should use, using another one. So like this here is kind of doing the edge detection if I just do this high pass filter here. So I have like this, all the edges here, kind of like, but it's not linked, not get kind of connected together. So let me get back to the chart here. Yeah. Okay. So so okay, what was another idea to do this high pass, not instead of high pass? I mean, to find this transition, what do we do? Like, so we know this is high pass thing, but we can do something even simpler. So if we think of like along this kind of like, if you look at this signal here, transition, like transiting across the edges here, um, I will have like a large change because it's a transition. I have a large kind of like derivative at that particular point, right? So one way to do the edge detection, therefore, would be like simply trying to do a kind of like derivative uh, in the sense because we are images, we are considering images, so we'll do a gradient of that image and then look for like the gradient that have large magnitude. So this is another example here. So like a realistic example, that's our earlier image. So if we go along this line here, if we look at the intensity here, and if we look at the derivative also like along this line here. So for the edges, I will have like large derivative, right? So from that, like we're able to sense the derivative. I mean, sense the edges. So, but the signal is like continuous, right? So sorry, like it's discrete, right? So instead of like doing a derivative like as you are in the calculus, we just approximate that, right? So for example, like we can approximate the derivative as like just a difference of like consecutive pixels. So this is a 1D case. We're showing a 1D case. So for example, like I can doing a forward approximate. So okay. By the way, like uh, so just I'm trying to move to my other desktop. Okay, maybe I click here is easier. Okay, now I'm able to do that. Maybe just again, like make sure that you guys remember like what's derivative, like why we get that. So okay, actually you saw that thing just now, but okay, let's say I have the derivative of fx here. So this is like a 1D, so x is like 1D here. So, and fx, if I take the derivative, that will be equal to something. Okay, maybe I ask like this. What was this below? Like this is equal to the derivative of fx. That's basically the definition of, you can think of like the definition of derivative really. So what's that thing in the denominator? Yes, okay, someone is, okay. Yes, that's delta. Make sure. Okay, well, why is delta? Because like, the derivative what it's doing is trying to measure slope, right? So it's really infinitesimally trying to estimate the slope at the particular point, right? So if I have a point here is x, so what I'm trying to do is I look ahead. Let's say if I go to x plus delta here, this is a at the location x and fx, right? Now if I move for delta, so I move up to like x plus delta and f x plus delta. I want to know like how steep is this slope, right? And the slope of something, like let's say if I have, this is a now it's a fx. Let's just call it like this is delta y here, right? And let's say this is a delta here. So then the slope will be simply equal to like delta y over delta, right? And that will be the derivative. And delta y here is actually just fx plus delta minus fxy. So yeah, so therefore like this is delta. So if we do a discrete very rough approximation, if we set delta equal to 1, let's say, then we will just get like fx plus 1 minus fx over 1, right? So that's why we have that approximation earlier. Oops, I want to move this instead. Yeah, so we have this approximation earlier. And we can go forward or backward approximation, or like we can just get a central that get that one step forward, one step backward. So therefore the delta now will be 2, right? So over by 2. So then we can have like a very rough approximation of the derivative. So this gives an example here. So if I do this as 1D like this, right? If I this is just a dual filter, right? So on that, then I get the derivative is it's just doing like as we do filtering like earlier. So I have this guy. So consider low padding here. We ignore this beginning and the end here. So this one, therefore, like, would be just equal to this thing dot product with this guy, right? So therefore, I will get like 15 minus 10, so it's 5 here. Then for this one, will be like this part here, do a dot product of this one. So I have like 10 minus 15 equal to minus 5. So this is another example here. So okay, I'll skip. I mean, but you can try. I'm thinking like ask you but it will be like a lot of typing here. That's fine. So, but this is apparent. So you see exactly detect an edge, right? So this is like an edge here, right? This is an edge because there's a transition here. If I apply this filter, it detect a horizontal, sorry, like a vertical edge. Okay, maybe this is a question I can ask. So how do I detect a horizontal edge? What filter I should use? So filter, say any filter to detect. I have horizontal edge. So just now, like we detect a vertical edge, right? So we detect vertical edge with something like 0, 1, -1, something like that, right? So how like if to detect a vertical edge, oh sorry, detect a horizontal edge. So instead of detecting something like this, if I want to detect something like this, so what should be the filter for that? Yes, but yes, it should be high pass. It should be high pass. And it's simply the transpose of this one. You just take it vertically, then you will get like that, for example. Or you can construct anything similar. For example, you can have like 1 -1 0 or something like that. It will detect the transition, right? Or I have like 1 0 -1, let's say, over 2, let's say. Then we detect the transition. And okay. I ah ah that's very annoying. Uh, why is I'm trying to move this window back down there. Okay, now I managed to do that. Okay. So no, but the signal is 2D, right? So therefore we should do an image gradient instead. So then you can have like basically use one of the filter we just mentioned there. So for example, like the one for this one to do a vertical edge, we need like this 1 - 1 to detect this vertical edge. Then I have like the transpose of that detect the horizontal edge. Then combine them, like I will have like two components there per pixel, like each pixel I will have a value, right? And then like the value actually will describe the gradient. And the gradient is like uh it's like it's basically it's the pointing to the direction that like you're getting the value is getting larger. So consider this is a 2D signal here. So the image is just a 2D signal here. So consider just this point here. The gradient here, the direction here is just pointing to the in this case to the direction that is like this pixel is getting brighter, right? Because brighter is higher. So this is exactly pointing like that is like getting brighter. Um, and from this direction here, so therefore from this gradient here, we can actually find the orientation of the edge. So for example, like if I have the here, like it's not very apparent, but this is, I say this is an edge here. So from this gradient, we basically point the direction of the edge. Um, and so of course we can find the angle, like, yeah, just like inverse tangent of that. And the strain of that edge then will be just the kind of the magnitude of the gradient. So um, this is again like illustration. So maybe another test again. So which one is the gradient for x direction? Just x direction. So I have like taking like, or like which one is I'm doing like, I shouldn't say, I mean, this is like really, I copied the slides from somewhere else. This is actually a bad thing to say. Like gradient is not defined like this way. I should say like derivative like in x direction. So no, actually it's just the opposite. Actually, it's like this one, because I um you remember that like if you take the derivative in the x direction, what we do with that, we do like we like we're drawing a line here. You think of like we take derivative along this direction, right? So you draw a line here along this direction, and we try to catch all the transition like along this direction here, right, horizontally, right? So and when do we have transition horizontally? When we cross through a vertical edge, right? So therefore, like it's really like this one is the x direction, like kind of like derivative. This is will be the y direction. They catch like the horizontal edge. So now if I combine this together, so if I just uh, combine the magnitude of these two together, I will just get the gradient magnitude more or less will catch like the all the edges. Like so this is like basically like that's what you get a simple edge detector. So but the problem is that if we use that from just this doing this alone, like I mean, basically I mean, horizontal derivative and vertical derivative, and then like compute the magnitude. Um, we may have problem if the image is kind of noisy. So for example, like if I have the kind of this signal is like quite noisy, so the derivative itself is like almost drowned into noise where you cannot see the kind of transition here anymore. So what we can do is that we can do some smoothing. So a simple idea can be like, now if I'm doing derivative, like let's say in one direction, maybe like I'm doing derivative in this direction, maybe I'm trying to smooth in the other direction. For example, this essentially just a low pass filter, right? So because you're taking average of like the two labeling pixel here, so then it will smooth out this output a little bit if I do that. Uh, and then like therefore like this essentially doing a horizontal derivative, but it's like doing horizontal derivative with a little bit of smoothing. So, and this is like the period edge detector. It's less common. Like if I just do like this, if I have this is like along this direction, the orthogonal direction is like applying like a Gaussian like filter. Then we have a Sobel filter, Sobel edge detector. That's it's more common. So basically, it's a very simple idea. Right? So you one side you do smoothing, the other side you do derivative. So then if you this is for of course like for the okay again like another check. This one will detect horizontal or vertical edges. Yes. This detect vertical edges. Yes. Um, yes. So okay, let's move on. So that then using the Sobel filter, or sorry, Sobel edge detector, it will be exactly the same thing as before. Right? So we have like the X component that is filtering with this one, and then the Y component will be filtering to exact the transpose of this guy. Then you can just compute the the sum of square of them and take the square root as the magnitude, compute the magnitude of these two components, and then like whenever G is big, then sufficiently big, we consider that is edges. And like before, like we can compute the orientation of the edges by the direction of the gradient. So and this is an example of the Sobel filter. So like I think yeah, this is like doing derivative in the horizontal direction. You get the vertical edges. I catch all the vertical edges. The catch like, and this like I'm doing like vertical derivative. I catch all the horizontal edges. Then I just add these two together. So square of this each of the element and square of each of these elements sum together. This square root and then like this gives the magnitude basically. And then so this you see the strong edges over here and there. So for Sobel filter, like um you actually this is like probably not just for Sobel filter, but Sobel edge detector. Uh, so many edge detector can have this kind of problem. Is like if you have like slow varying edges, like you may not do too well. You may not be able to catch that. Um, and yeah, actually, like with this, like you may either not catching that if you set the threshold is too small, sorry, too big, um, or if you set the threshold is too small, you will just get a a fake edge here. So in that sense, people will say this is a poor localization because you probably just want to get one edge, but you get like multiple edges here. Um, so okay, but uh, depends on like what you're expecting. You can kind of like control or like um, kind of tune it a little bit by adjusting the smoothing effect, right? For example, if the image is quite noisy, so then you can apply a stronger filter or like stronger smoothing. In the sense that stronger smoothing will mean that um, if the image is noisier, then here I will just take a more pixel to smooth out vertically, let's say, then I will get more smoothen edges. But in that sense, you will get like a poor localization of the edge. So you get a pretty thick edge here. So if your image is not as noisy, then maybe you can set the kind of the smoothing effect to be smaller. So another like very popular way to do, or like you can think of the Sobel filter is a little bit ad hoc way. So we can do in general, like if you think of that in general, it's like we can always solve this noisy problem by just doing like filtering, low pass filtering, and then the edge detection. So for example, like I can say use Gaussian filter that is like most popular. I can first I do a Gaussian filter, and then I will do the take the derivative, right? Um, and note that like if I use the Gaussian filter, like uh, I of course I can do that, or like any other filter in general. I can I can combine like of course this is like two steps, right? I first I do a filtering, and then I do a derivative, right? But actually I can combine these two steps together. For example, like if I think of like I'm doing a filter like with this a kernel like G here, so then the convolution is something like that. If you remember last, okay, it doesn't matter. This is like just doing, this is just doing a dot product, right, essentially. But I flip the filter first, right? If I don't flip it, I will have like x plus x pi here. So then this is convolution. Then you see that I'm taking derivative along x, right? But here the integral is over like x pi here. So therefore I can have the derivative go inside, and this actually f x pi does not depend on x, right? So only take derivative of this guy here. So then you can actually think of this as a new function. It's like I have like actually this is actually like doing a convolution of x pi of this derivative of this g function here. So of this dx dg here. So therefore, like instead of I'm trying to, you see here, like first filter here with this g and then take the derivative, I can just say directly filter with this dg dx kernel here. So then we become just one step. So if I use this Gaussian filter, then I will have the resulting will be like some derivative of Gaussian filter like this guy here. So the original Gaussian filter like this, the derivative of this will be like this, going up and down. By the way, it confused me also a bit. Like in the past, like there's like dog here. Whenever people say dog, like it can be like actually difference of Gaussian. That's we will talk about later on. But here is a derivative of Gaussian. I try to avoid using dog here because yeah, dog. I guess like difference of Gaussian is a little bit more popular than common than derivative of Gaussian. So I have this. So okay, like I have the filter, I can take derivative in both like x and y direction, right? So therefore we have this derivative. That's exactly what you see at the beginning. So we have this derivative of Gaussian uh, filter. That's one of them. If you remember the first slide there, right? I forgot this is A or B. I guess that's the A figure or something like that. And and yeah, and then you basically do the same thing. You're going to have the image filter with this component and filter with this component, and then you add them together. Look at the magnitude. If the magnitude is sufficiently large, then we will have the edge detected. And compare with like Sobel and like this derivative Gaussian, note that like for Sobel filter, we're only smoothing along one direction here. And if I use derivative of Gaussian, I'm smoothing like along both directions. It may be good or bad. Like I will show you a demo, then you will decide yourself basically. I mean, it turns out like all of these are not as good as a very common edge detector, the Canny detector that is, but you'll see about that. So this is a DOG result here. So it's decent, I guess. So as we mentioned earlier, like, but we didn't get into detail, like what contribute to a good edge detector. So we want to, there's a couple criteria, I guess a reasonable criteria people figure that out. So first, you want to actually close the ground truth, right? So this one is too bad, like it's not even close. And the second one I mentioned already, you want to have like reasonable localization. So in the sense that you want to have the edge is like actually same thing. Like um you in the sense that you actually like refer localization as this one, I refer to this one. So anyway, so your localization, I think this is like quite close to this one here. But I guess like here we refer to the fact that maybe it's not an edge, but you just kind of like have false positive saying that okay, that's an edge, but actually it's not really an edge. Or like you have false negative that it's an edge, but you do not consider as an edge. But the localization is like you have the edge here is actually the edge, but it's like just not get close to the real edge here. Or like in the case that this is actually, I shouldn't say localization earlier, I should say like this is like we should have a good um, kind of like single response case. Like we don't have like too many responses. So if you have like just one edge, you don't want to have the mm, looks like a very thick edge like contain like many responses there. So Canny detector is mainly trying to kind of like solve this, I guess, or like a little bit of like these other things as well. So basically, Canny detector is based on like DOG. So therefore, why I like to talk about this derivative of Gaussian. So it is basically like, okay, just as we mentioned earlier, we have the DOG detected the both horizontal and vertical edges, and then we combine together, right? We'll have this, just look at the magnitude. So we have this initial approximation here. And then like afterward, we want to figure out like, we don't want to have the edges too fake or whatever. So we want to reduce like some of this, I mean, remove some of this fake response. So what we're trying to do here is like, we will do some long maximum suppression because like, if you think of the edge here, like this edge here, so we want to have only the one that is the maximum response will be taken, and the rest will just not consider as an edge. So how we're going to do that is like, if we detect, like for example at this point here, if we detect like this an edge here, so we go perpendicularly, yeah, perpendicularly, yeah, is that a word for that? Okay, along that edge. So then that should be like should be a transition, right? And also like if you look at the magnitude of the DOG response there, the magnitude should be maximum. It should get larger and then go to the peak at exactly at the edge, right? So we simply should just like remove any point that is not supposed to be maximum. So how we're going to do that? We will just like for all the response there, like let's say if this is one response here, then we go along the direction of the gradient and just do interpolation. Let's say like look at for let's say for this point here, look at the the um, the response at P and R. Approximate. Of course, I don't have response for this guy, but I can do interpolation. Right, I have response for this one, my response for this one, so I can interpolate to get result for P, and I can interpolate to get result for R. Uh, by the way, maybe I should elaborate a little bit. Yeah, just make sure you mean what I mean by interpolating that. So let's say I have this part here, right? I forgot like what's I I don't have automatic man. I think it's like P something like that. Maybe this is R or something, right? It's R. So let's say this is 0.4 and this is 0.6 here, and this is 1 and this is 3, let's say the value. So what should be value of R? Hey, are you guys still here? So do you get get my question here? So I have this is like the okay, let me repeat the question. So remember, like we have the response like for gx and gy doing the filter, right? So then afterward, like uh we have get this value, like that is like my g value, like the magnitude, or just call it g magnitude. So this g magnitude, I know the g magnitude at this point, and all the points here. Now let's say the g magnitude here is 1 at this point and 3 at this point. Now I count like this is the gradient here, like along this direction here. So I want to find what is the value, the interpolate value of this R here. So I know this is like 1 here, I 3 here, and then okay, this is not exactly in the middle. So this is a 0.4 and 0.6, let's say. So R is, let's say, what I mean is let's say this is this point is a 1 1, and then this point here is a 1 2, and this point is a 1 3 here, the coordinate, and R is at the coordinate 1 and 2.4, something like that. Okay, let me draw it again. Erase something, then I can draw it again. So you just need to look at 4 points here. Like let's say I have 1 point here that the location, the coordinate is 1 1, and the value is 1. Now I have another point, maybe I draw farther away, so I have more space here. Another point is like this is 1 2, right? And then this I have point here like 2 1, and my point like 2 2 here. Now I need to interpolate this point here. Here like it's like 0.4, the distance is 0.4 and 0.6. That means that the coordinate here is a 1.4, let's say. Actually, I changed the coordinate from here. Let me erase this one so I won't confuse you. 1.4, let's say. So what this is 1, this is 3. So what will be this value, the interpolate value of this guy here? So is that clear now? I mean, the problem itself, is that clear now? Yes, yes, actually, that's probably right. So no, you don't need to worry about the square root there. So we already this is already the g bar value here. This is a g bar value. So um the simplest way, of course, you can do like some weird fitting, but the simplest way, like do interpolation, you just do a linear interpolation here. So therefore, like if you think of like wow, you get some amazing value there. So if I just here, like this is 1, right? This is 3. So if I do a linear, so think of like this is 1, right? This is 3. I horizontally draw that, right? This is 3 here. Okay, how do I mean, if I do a plot here, this value go from 1 to 3, right? So if I linearly interpolate, right, this is a distance is 0.4, this is 0.6 here. So then the value, the height here should be this height times, should be, let's say this height will be, I call it h here, should be this height time 0.4 over 0.4 plus 0.6, right? Or like this is actually just 1, right? So, and so therefore like this value should be like this h times 0.4 plus 1, right? This offset here is 1. And h here is actually just 2, so it's like 2 times 0.4 plus 1, so it is 1.8. Yeah. So, okay. So then we know the interpolate value here. So I know value here. I can interpolate value here. So I just look at like whether this guy and this guy is bigger or smaller than this guy. Uh, yeah, you don't need to do the square root. Okay, you may I don't know, that will be tricky. Do some fancy interpolation. For example, like I can do a bilinear interpolation, something like that. Um, oh, this is already bilinear. I mean bicubic. If you remember, like last time you have this bicubic formula, for example. So because if you have linear interpolation, like so the we assume the plane is continuous, but it's not smooth. So we can like fit a polynomial, but it's too much. Typically, like it's not necessary. So therefore, it's just do a linear interpolation, like what we discussed earlier. So and anyway, so this one here, yeah, as I mentioned, if this guy is like is bigger than like both of these, then we keep it. So if like oh, okay, yeah, because we want to do this long maximum suppression. So let's say here, like all these are responses. Like after this, let me just that's how I can. Okay, I guess the easiest way is I just do a screencast, screen copy. That's, oh, maybe I copy this entire thing here. Maybe useful. So basically, when we try to detect the edge here, what may happen is that we may have loss of response. We just want to detect one edge here, but we may have like several pixels, like for example, like all these red pixels here is like correspond as the edge. So maybe like this blue one are not edge. Oops, let me dot a little bit better here. Yeah, but you see my point here, right? So then I have a pretty, maybe I make this red also. I have a pretty thick edges here. That is not very preferable. So what I want to do is I just want to detect just one edge here instead of like I have all these pixels considered as edge. So what I'm trying to do is I will erase some of the response here. So for example, like for this guy here, it may not be an edge, or like most likely I only consider as an edge if along the direction of the gradient. So because we from the G we know the direction of the gradient, right? So let's say the direction of gradient is like something like that. So only if like this guy is bigger than this one and this one here, then I will consider as an edge. Otherwise, I mean, consider this as a point contribute to an edge. Otherwise, I will, remove that. So then the outcome will be like, I probably only have like this one is edge, this is edge, this is edge, and so on. So for many of these words, I can get removed. So did I answer your question, I guess? And we need to do interpolation because I need to go along the direction of the gradient. So the gradient doesn't necessarily to be like just exactly diagonal or like exactly horizontal and so on the direction. Yes, you can think of that way. So it's like eliminate this unwanted response. So this like is also considered as edge response, but I just want to have like a one kind of like one line to represent that or one curve to represent that as instead of like a thick kind of like much thicker line. So that so hopefully okay, again, I need to pull this down here. Always forget about that. And so yeah, I guess this illustration is easier for you to realize that. So this is exactly what happened. Like no maximum suppression, I would guess this way. If I use a maximum suppression, I remove loss of response that I don't want. So it's like have a more precise kind of like detected line here, detected edge here. So another contribution of the Canny detector is like there's some they call it hysterious thresholding, but I think it's better name is just adaptive thresholding. So what they do is like they try to connect edges together. So for example, I may have like edge pieces. So I don't I will start with what they're trying to do is like they try to start with like places have like very strong response, then you can for sure think that this is an edge. Then starting from there, like you just go along the line that trying to look for like edges, like continue to go along the edges. So we can do that because we know the gradient, right? So, and if I know the gradient is this direction here, I know the edge should go in perpendicular, right? So therefore, if I mean, if my currently processing at this point here, then I know the uh, next point, if I go along the edge, will be either this one or this one. So therefore, I can just go, I mean, try to see if like these 2 points also like correspond to edge. So if they are, then I'm going to continue to move on and so on. Um, and uh, and also like uh, they when I say this, like they have like two thresholds to control that. So when you have the edge magnitude or the gradient magnitude is sufficiently big, like larger than a high threshold, then we consider it's a strong edge. Then we don't actually need this even. So we will always consider this as an edge. That's fine. So if it's small, if the gradient is small, but it's like still bigger than a okay, yeah, if it's still bigger than a low threshold, then we will consider it's an edge candidate. If it's smaller than the low threshold, then it will be just considered a noise. Then we just ignore that. So then like basically what you think of is like if I have go along this line here, if this point if like the gradient is too small, then I will just ignore that. If the gradient is sufficiently bigger than the lower threshold, then I will just continue to try to extend the edge. So that would be like this. We start with some strong edge here that's bigger than the uh, high threshold, and then like uh, we will continue to try to connect the edges like, along the low threshold. This low threshold, I mean, for for um, for the uh, for the point with gradient larger than the low threshold. Basically, this is the point that is less than the high threshold but larger than the low threshold. So this will be like the result kind of like looks good. I don't know how this T low and T high, basically in OpenCV, they have a different kind of unit for this threshold apparently. Uh, if I test that, it has the value is like 100 or something. I don't know how they, yeah, but anyway, like you can test it out basically. So this is a effect like changing the spread. So if you have like larger smoothing at the beginning, then you will of course, you will eliminate more edges right at the beginning. So you have like three parameters you can tune basically. You can have like kind of like change the smoothing uh, coefficient, or like you can change the threshold also. I just mentioned the thresholds, the stronger, the larger threshold and the high threshold and the low threshold, like this one here. So and that's it. Yeah. Okay. I guess um that's actually beyond Canny detectors. Like Canny detectors, is a work in the 80s. Like there's still like lots of works like afterwards. But I don't know. At least I don't work on like edge detection. I don't feel that it's exactly a very much active research area, but it's something that like you will use like all the time. Basically, it's needed like a very important component, and always just use edge Canny detectors, even though like that's much better one, I guess. So you may try out. Like, I'm not sure. Like maybe you can search over like OpenCV, like see if like they have like other Canny detector available. And so I guess I will just give maybe here. Oh, by the way, like we have homework assignment. I guess you should have aware of that. Another assignment due like a bit more than 2 weeks. That's basically trying to do like what we demonstrated last time, like do a hybrid image and a general hybrid image, or like generate and also generate a composite image, composting image. Um, and let me give a demo of this edge detector here. Is that here? Let's look for that. So here you can see I put 3 detectors I will describe like uh 3 detectors here described earlier. So we have the simple super edge detector. If I change the basically like if I change this is like the size of the filter, like the smoothing filter. If I make it bigger, then it's smooth. Okay, it's supposed to. Okay, I don't quite understand why it's like. Okay, I guess I maybe the parameters doesn't mean that. So I'm changing a parameter to Sobel. Let's see. Let's see if I can open a other terminal from, because I have some homework solution in my template there. I don't want to be by accident just show you the solution. So let me just start a new Jupyter notebook. I have some untitled here. Let's see. I think I can use this untitled maybe. Do not need to. So let's see. I use this function as CV2. Let me, yeah. Oops, I want to turn off my Cantonese input here. So you can just, oh, it doesn't have, oh, Sobel. I don't spell it correctly, I think. So I changed the kernel size. Actually, I changed the kernel size. Let's see what parameters I. Yeah, okay. Anyway, like you can read the API there, like read the description of the API here. Okay, I'm not going to bore you with that. Oh, I have a wrong kind of like typo here for Sobel. So and this is the DOG. So also maybe I should, let's see if I can just find something more interesting to see. Maybe this one maybe half like this. So uh so you can see the effect if I change uh the kernel size there. So if this one is apparently this the parameter is exactly the smoothing here. If I have the kernel size bigger, then it's getting more and smooth out more and more. So therefore, like the edges just you won't detect as many edges. And Canny detector here, I only set a check bar for this high and low threshold, but you can see the effect basically. If I set a high threshold, I just eliminate more edges candidate because one of that is a strong edge, the other I guess is a weak edge. Let's see. Yeah, it's hard to tell which is which, honestly, but it's like something you can you can play around, and it's good to play around, and and okay, and one more thing, I guess I maybe like before we leave, uh, we should schedule the presentation. So you guys should submit your presentation kind of abstract, like for the graduate students, submit the presentation abstract like this weekend. And so we need to schedule you guys presentation. I only do one time. So I have a small script here to do a lottery for your dates. So I'm thinking, okay, you guys, okay, at this moment, let me know why are we like, do you guys like have any problem with this 2 weeks? Like anyone like for the guys like who are going to go present that, like this is okay for the undergrad. If you have problem like attending, like it's kind of okay. You should, but you get involved because I expect like everyone is going to give a peer review for everyone for every presenter. So, but it's important that like for the presenter, they are able, of course, uh, make sure that you have to be able to present like, on that day. So I have these 4 days here. So um, typically we will have like 2 presentation per day, but per class. But this time we have like quite a lot of graduate students. I guess it's better to have like 3 presentations per class, and but that would be like quite tight, honestly. Like you will have to control your time really well. So it's like your presentation should not be longer than 25 minutes. So should be around 20 to 25 minutes. And then like in case anyone have any questions, it's good to but you don't want to be less than 20 minutes because like most likely yeah, I don't think like actually 20 minutes is very short, like especially if you want to explain something. And you probably will need to uh, really like, okay, anyway, let me just like run this first. So this is the schedule now. So I will copy that like on the website, but you guys can kind of like, okay, if you're around here, just like take a note of like when you're going to present. So we say will be like the earliest one will be 2 weeks from now, not actually more than 2 weeks from now. Um, and and uh, and for your okay, yes, and for peer review, what I'm going to do is I will post as an assignment, like for yes. I have some kind of rubric for the project, I guess, but it's a rubric for yeah, okay, it's okay. The rubric will be given like later on. So for the report, so um I for the some, but it's the rubric is like actually mostly on the written writing, um but it's actually is for the it's actually basically a bit like common sense, like for the rubric, for whatever I'm going to fill in for the rubric there. Uh, Basically, you expect, okay, for the project, I am looking for you put into a bit of effort, like, and because the scope here is like can be pretty wide, you can do something like really, really research. Let's say you're trying to do something, okay, no one did before. So then in that sense, I don't expect you can will be have a really kind of like complete final product, right? You maybe like you're trying to improve just like edge detection, and then it decides that it's totally okay to have just like what I mean is like not a complete kind of applications that is built out, right? But on the other hand, if like you have something like using like some online packages or like open source packages to do like all this heavy lifting already, so then what you're trying to do would be like more or less using your OpenCV skill or like how to build like application to build something that is something interesting, right? So that would be like two very different projects. I think both of them are valid and both of them are interesting. So therefore, like, uh, will be more like if in general, like, uh, yeah, I guess I mean, like the rubric, like even I give you, even put it down later on, will be more like on what kind of like components to be included in the report. But in terms of like the scope of the project itself is more or less like what I meant, just what I said just now. So it can be very broad. So like um, you can take very different directions basically. But you for the report, of course, like it should be clear enough like what is your contribution, right? What you actually done. So you need to convince the readers that you have did something, right? It has to be like give a reason why you want to study that, and hopefully like if this is a if you are claiming to be something lawful, then like you need to do some literature search, right? If you claim okay it's not lawful but I'm trying to do some interesting application for something, then hopefully something like the application is kind of useful. So therefore, like in terms of the scope, it's hard to give like a rubric for that. Like, but the rubric like I'm going to give will be more like what components should be included in your report. So for example, like very laterally, if you are trying to write the kind of like the intermediate report, what do we call that? Like the progress report there, it should include components that like what have you done so far, right? Why you actually maybe it doesn't necessarily do it. Maybe a brief like explanation like what you try to do, and then what have you done so far, and then like what you plan to do next, right? So that will be a very lateral progress report, and the final report will be very lateral to include like why you want to do that and what you have actually done, and then convince that like you actually give some effort to do that, right? So any questions like for the I will include a rubric later on for when it's where yeah I'm trying to do for the progress report and the final report, but will be more or less like what I just said basically. But I probably put in a little bit more detail, but um, yeah, in terms of the scope, it's hard to put into the rubric honestly because like, that can be very kind of like different kind of projects are acceptable. Like so, I guess I do you guys have any other questions? Uh okay. Topics. I guess I hope I just explained that. I have someone asked what type of topics. That should be topics that related to the computer vision, right? So um for example, you cannot do like stock prediction, for example, here. So I do it, even though I'm quite interested, like for example, I want to predict the stock price in the or like Bitcoin price like, for the next 50 days or something like that. It's an interesting project, but it shouldn't be a project for this class. So and as I said, like if I will have instruction for okay, I will have provide a rubric like for but I mean like uh I will try okay. I will see like what okay like for the project maybe I write a couple more description like maybe like somewhere. So but it's more or less like repeating what I just said basically. For the grad presentation, it's just presentation. So is there's no way up. But I want you to just weigh up this like kind of like presentation abstract like ahead of time, so at least you thought about it. Honestly, that's I won't give any penalties if you in the last minute you change your mind. Say, I try to present this, but I can't understand that. Instead I try to present this instead. So that's fine. But I just want you to start early, basically. At least I give some thought like what you plan to present. Yeah. So therefore, like have you guys submit a presentation abstract at least 2 weeks before ahead of time, ahead your presentation? So any other questions? So and if not, I'm going to see you guys next week then. Yeah. Yeah, thank you for attending. So